In this video, we're going to learn about alkene synthesis. First, we're going to learn about, or review rather, reactions that can give us alkenes, which we learned in the previous chapter already. So what starting materials and reagents and what processes give us a double bond, create a double bond or give us an alkene. And then we're going to go into how or what alkenes are further capable of giving us. What molecules are alkenes capable of making, or what reactions are alkenes capable of going through. And by the end of our discussion, or the next few sessions, we should be able to put together an alkene roadmap, which should be a combination of all the different reactions that can give us alkenes, or of which alkenes are products of, with the appropriate reagents, and which also the reaction roadmap should also connect us to all the different reactions that alkenes are capable of going through and all the different products that alkenes can give us. And we can further expand this roadmap to combine the other reactions we learned by adding more reactions to this, which we should be able to complete this roadmap by the end of the semester and make a comprehensive roadmap. It should be a combination of all the reactions and all the functional groups that we've learned. And such a reaction roadmap, or an understanding of such the relationships between such reactions, is very useful in doing synthesis problems, which are typical organic chemistry exam questions, where your professor can give you, using your, sometimes you'll be given the limited starting material, using your reagents, and given the product, we need to work backwards and find what steps can lead to our desired product. That's just a general example of synthesis question. We'll do more examples later. So we start off by reviewing elimination, which is a type of reaction or a class of reactions that we learned about in the previous chapter. One of the ways in which a double bond is made is through elimination reaction. And in the previous chapter, using alkyl halides as a model, or as an example, we learned that an alkyl halide, which the definition of which is it's an sp3 carbon bonded to an X. And for an elimination, our requirement is there must be at least 2 carbons present, because the double bond can be only between at least 2 carbons. So in the previous chapter, we learned that in the presence of a base, which abstracts a proton from the carbon adjacent to the carbon holding the X. So the carbon holding or bearing the X we call the alpha carbon. All the carbons directly adjacent to that carbon are called beta carbons. For simplicity, in this case, I've only included one beta carbon, but there could be many more. So the base abstracts a proton from the carbon adjacent to the carbon holding the X. The CH bond density moves between the 2 carbons. The CH bond electrons move between the 2 carbons, and the leaving group leaves. These 3 processes could happen all in one step, in which case we call that a concerted reaction mechanism, and that would be E2, or it could happen step by step, which would be the E1 mechanism and would involve more steps. For a review of E1 and E2, or the difference between E1 and E2, you can see my other videos. that talk more specifically about that, but this session is assuming that we have previously discussed and gone over elimination, the basics of elimination reactions in more detail. This is just to review. So such an elimination reaction that we used in the previous chapter to learn about elimination, this is called dehydrohalogenation. So dehydrohalogenation, which is the reaction we just showed, is just a type of elimination reaction, and the base, again, to review, the base attacks the proton adjacent to the carbon. The base attacks the proton bonded to the carbon adjacent to the carbon holding the X. The CH bond density, the electrons in the CH bond move between the two carbons, and the leaving group leaves takes the CX bond electrons with it. As a result, we have a pi bond between the two carbons, which has been created by the CH bond density. And all the other groups that were attached, whatever was attached here, which I've left out for simplicity to avoid crowding this, and whatever was attached here, this. The rest of the four attachments remain attached as they are. And we have an alkene, we've created a pi bond, and the elements H and X have been removed. Now, as we will soon see, this is only one kind of an elimination reaction, the alkyl halides going through elimination in the presence of a base. Many more molecules, like alcohols, are able to also go through elimination, which also gave us alkenes, but the groups that are removed will be different. They might have additional steps, they might differ slightly, but overall they follow the same general pattern. Now we're going to focus in this session on how to make alkenes or what conditions, because as we previously learned, I'm going to also review the differences and similarities between a nucleophile and a base, and how we can choose, because as we also learned in the previous chapter, an alkyl halide is also very capable of going through a substitution. So the same molecule, the same alkyl halide, if you remember, can go through a substitution in which all that happens is that the leaving group, or the X, is replaced with the nucleophile. If you treat this with a nucleophile, it can lead to a substitution reaction. Or if you treat the same reactant with a base, it can give an elimination product, which will be an alkene. So in this session, one of the things we're also going to learn is what factors can be used when we're doing synthesis questions. So if your professor gives you a question on the exam where you have to make an alkene, and from a given starting material of your choice and indicate the steps, what conditions can we choose that are going to avoid substitution and that should favor elimination? Because we don't want, as we just said, that SN and E2, SN2 competes with E2, SN1 competes with E1. SN and E elimination are competing reactions. So how can we ensure, if we need depending on the product we need, how can we ensure that we get the elimination product in a higher yield or in a greater amount, and how can we prevent the substitution product from forming? One of the things that helps us do that is, so I'm going to label this list conditions. that favor elimination or alkene formation. First thing I'd like you to think about is, or remember, if we know we're doing elimination to make an alkene, is there a difference between E1 and E2? Well, there is a difference, but is there a difference? Should we favor one or should we go for one more than the other? And the answer is yes. E2 is preferred because E1. So the way we'll mention this is E2 better for making alkenes because E1 has more competing reactions. The next thing we can talk about is the substrate. If you remember, so now that we've decided that we want to go for E2, the competing reaction for E2 is SN2. So usually E2 and SN2 go hand in hand. How can we ensure that the substitution is eliminated or the substitution is reduced or prevented and the elimination is the main reaction? If you remember the reactivity of the substrates that are the best for elimination are the poorest for SN2, which are the tertiary substrates. If you remember from the previous chapter when we did alkyl halides, the tertiary substrates which this is an example of, were the poorest for SN2 reactions because SN2 reactions require nucleophilic attack from the backside of the leaving group, and all the steric hindrances does not allow SN2 to happen for tertiary alkyl halides or for tertiary substrates in general. But these also, the tertiary substrates, are the best for elimination. So if we choose our substrate to be a tertiary substrate, then we can ensure that elimination will be favored over substitution. Because these are the least likely to go through substitution. The next thing to consider would be the choice of base. And over here I want to talk about the similarities and the differences between a base and a nucleophile. Well, we want to choose a strong, bulky base, which is a poor nucleophile. This will also be a way that we can prevent the substitution reaction from happening, and we can favor the elimination reaction. Because substitution requires a good nucleophile, and elimination goes through is favored more when a good bulky base is present. And this step, or this keeping this in mind, or this choice is especially more important when the substrate is not secondary. For example, if it's when the substrate is not tertiary, for example, in a secondary substrate. If we want for a secondary substrate where the X is attached to a carbon that has two other carbons attached to it, secondary substrates tend to be able to go through are as likely to go through substitution as they are through elimination, and if we're not choosing a tertiary substrate, if we're choosing a secondary substrate, then this consideration is even more important. I'm going to break up the discussion in the differences between what the differences and similarities of a base and a nucleophile in a separate video, just so that for the people who understand, if you understand this completely, because this is supposed to be just review, if you understand this point, why we choose a bulky base or why bulky bases are poor nucleophiles, if you understand that, then you don't have to go through that again. And if you don't understand that, you can go back to the clip that I'm going to make on just the discussion of basicity versus nucleophilicity, or the similarities and differences of basicity and nucleophilicity.